Welcome back. I hope you took your best shot at this Build Your Understanding problem. If not, I strongly encourage you to stop watching right now and go through it yourself. I'm going to go through it pretty quickly. You may find if you didn't get numbers right that you need to pause the video and see what my numbers are. But basically, the range for the population data would be 90 minus 67, which is 23. Then we have our column of x's. Those should have added up to 451. So your mu would have been 75.17. Then you have your x minus mu column, your x minus mu squared column, and at the bottom of that last column, your x minus mu squareds should have added up to 358.84. So then your standard deviation sigma would be the square root of 358.84 divided by n, which is 6, and you get 7.73. For the sample data, again, we have our x column. Your x's should have added up to 211, so your x bar, the average, would be 70.33. By the way, did you remember to use x bar here for the sample and mu for the population? That's actually important. Then we have our x minus x bar column, our x minus x bar squared column, and your x minus x bar squareds should have added up to 18.67. So then for the standard deviation, we'd have the square root of 18.67 over 2, which works out to be 3.05. The range is 6, 73 minus 67. The last topic in this section is a theorem called Chebyshev's theorem, and it is a kind of a remarkable theorem. It tells you where to expect data points to be in a data set if all you know is the mean and the standard deviation. And I've gone ahead and used the notation for populations here with the mu's and sigmas rather than x bars and s's. But Chebyshev's theorem actually works for sample data too. Chebyshev's theorem is actually a formula, but I don't think the formula will be that helpful to us. So what I've actually presented here is some of the information that the formula would give us. For example, it tells us that at least 75% of all the data values fall within 2 standard deviations from the mean. In other words, the interval from mu minus 2 sigma to mu plus 2 sigma. At least 88.9% of the data falls within 3 standard deviations from the mean, and at least 93.8% of the data falls within 4 standard deviations from the mean. I think this will make more sense if we see an actual example. A data set has mean mu equals 50 and sigma equals 8. Find the intervals where at least 75%, 88.9%, and 93.8% of the data must lie. So Chebyshev's theorem says at least 75% of the data lives between mu minus 2 sigma and mu plus 2 sigma. With these numbers, that's 50 minus 2 times 8, so 50 minus 16, which is 34, and mu plus 2 sigma would be 50 plus 2 times 8. So 50 plus 16 is 66. At least 88.9% of the data lives between mu minus 3 times sigma and mu plus 3 times sigma. So with these numbers, that's 50 minus 3 times 8, which is 26, and 50 plus 3 times 8, 50 plus 24 is 74. And then at least 93.8% of the data falls between mu minus 4 sigma and mu plus 4 sigma. With these numbers, that's 50 minus 4 times 8, so 50 minus 32, which is 18. mu plus 4 sigma would be 50 plus 4 times 8, so that's 50 plus 32, which is 82. Let's get sort of a visualization of what that looks like. So I've put the mean mu in the middle. 50 plus sigma would be 58. 50 plus 2 sigma we've computed is 66. 50 plus 3 sigma is 74. 50 plus 4 sigma is 82. On the other side of 50, 50 minus 8 would be 42. 50 minus 2 times 8 we said was 34. We have 26 and 18. So Chebyshev's theorem says that 75% of the data will be living in that interval between those two numbers. 88.9% of the data lives between 26 and 74, and 93.8% of the data falls between 18 and 82. And I should have been saying at least. So Chebyshev's theorem, for example, doesn't actually say that exactly 75% of the data lives between 34 and 66. What it actually says is at least 75% of the data lives in there. This interval between 34 and 66 is described as within 2 standard deviations of the mean, because you don't go any further than 1, 2 of those sigma values, which is 8 in this case, either to the right or to the left. So you have not gone further away from the mean than 2 standard deviations. That's what's meant by being within 2 standard deviations of the mean. The interval from 26 to 74 is said to be within 3 standard deviations of the mean, because you don't go further than 1, 2, 3 standard deviations away from the mean in either direction. So that's where that terminology comes from. Now, because Chebyshev's theorem says that most of the data lies within certain distances away from the mean, that gives us a way of telling, or at least suspecting, if a data value is an outlier. For example, one indicator of a possible outlier is that an observed data value is more than 2.5 standard deviations from the mean. If a data set has a mean of 100 and a standard deviation of 20, would 160 be a suspected outlier? What about 140? We're told that mu is 100 and sigma, the standard deviation, is 20. So going 1 standard deviation away from 100 would bring you to 120. Another standard deviation would be another 20 units. Another standard deviation would be 160 units away. Now, what we're told is that one criterion for suspecting that something is an outlier is if it's more than 2.5 standard deviations away from the mean. So, in other words, starting at 150 and heading out further than that is a region of possible outliers. On the other side, going 1 standard deviation down from 100 would bring you to 80. A second standard deviation down from 100 would bring you to 60. And a third would bring you down to 40. 2.5 of those down from 100 would be right at 50. So the region below 50 is a region where if you have data values in there, you might suspect that it's an outlier. So what are our numbers? 160 and 140. So 160 would possibly be an outlier. It's in that region where the numbers are a little bit suspicious. Whereas 140 is not. It's not in the suspicious region. So we would say 160 would be a suspected outlier using this criteria. But not 140. I'm a little worried you might be wondering where I got those numbers 50 and 150 from. I was counting off standard deviations. You could compute that directly. So to be not below 2.5 standard deviations of your mean, in this case would be 100 minus 2.5 times the standard deviation 20. And if you did that on a calculator, you'd get 50. And similarly, mu plus 2.5 times sigma would be 100 plus 2.5 times 20, and you could do that on a calculator and get 150. So I did it by just counting off standard deviations, but you could do it that way as well.